Yeah, one thing I did not discuss over here is that this is why it is ortho and para, because over here the chlorine group which is attached is ortho para directing. This is ortho para directing to a electrophile. Okay, to electrophile. Incoming electrophile will go either at a ortho or at para position. So this is para position and this is ortho position. So that's it. Okay, let's solve this series of questions. First reaction, it is SOCl2. Whenever it is SOCl2, remember that it is a source of source of Cl minus. It is a nucleophile. Okay, so here nucleophilic substitution is going to take place. In the first question, it is a nucleophilic substitution is going to take place. So nucleophile is going to get substitute over here. See, this is cyclohexane. I'll write it this way. This cyclohexane is actually a bond line structure. It is written over there. This is a cyclohexane. Here it is oxygen and here it is hydrogen. This is what the thing is. Here there are two hydrogens. Here there are two hydrogens. Two hydrogens, and there is one hydrogen over here connected, right? Because all the valency of the carbon should be satisfied. So what will happen in this, all the carbons, if you compare among all the carbon, this is the only carbon which is partially positive because electronegative element is connected to that. So this is Cl minus. It is going to go and attack on this carbon. It is going to attack on this carbon only. And the next part is what? See, in every reaction, when I explain you, one thing you should know is what is electron rich and electron deficient. We always make this. I use this many time. Electron rich and electron deficient. So here this is the electron rich, electron deficient. Once this is done, next is which bond to break. Always remember that weakest bond we are breaking, right? Weakest bond we have to break. So weakest bond over here is the longest bond. Carbon oxygen is the longest bond. How do we know that? Based on the atomic radius. If you know the positions of all these atoms, you will get to know what would be a bond order. Not an exact value, but you will able to relate which bond is longer, which bond is shorter. So this is the bond which is going to break, and that's how the reaction will go. Means my final product is this CH2, CH2, CH2 over here. I've written this open, like all the carbons and hydrogen I have written just for your understanding. Some students, if they are not understanding like bond line structure, they can learn. This is a best example to learn a bond line structure. This is Cl. The OH is gone. OH minus. Um, okay, we'll do with the next question. I'll do that on the next page. Yeah. Here, next question is this. They have given a compound. The compound is this. This is CH2. This is CH3. This is NO2. And this is bromine. Can someone tell me what is this reaction? Bromine, heat, or light? Okay. Answer is whenever you see this reagent, it is a free radical halogenation. Free radical means it is not a electrophile, okay, nor it is a nucleophile. Remember this. Free radical will not happen over here, will not happen on benzene. Okay, it is very difficult to replace these hydrogens. So it will happen on this. Means free radical halogenation will take place over here. This is NO2. So this is CH2, CH3. So here there are two possibilities of the free radical formation. One is on this carbon, another is on this carbon. So I'll write both the possibilities. CH free radical CH3. This is one possibility. And other possibility is this NO2 is there. Huh? This NO2 is there. I'm just writing a one step of the free radical halogenation, right? I'll mark this as a A and I'll mark this as a B. Among this, which free radical will be more stable? It is this is more stable. This free radical is more stable because it is into conjugation. Pi, sigma, and free radical. This is what the conjugation is. This is less stable. Pi, sigma, and free radical. See, conjugation means there should be either pi, sigma, pi, or pi bond, sigma, lone electron, pi, sigma, negative, pi, sigma, positive. These are the most stable, uh, intermediates we can say. Like this will take place. This is in the conjugation. These systems are into a conjugation. Uh, so here, because of the conjugation, because of the resonance around a free radical, this is more stable. This is more stable. This is less stable. So final product will be this. Final product is BR. This is the final product over here. See. Next question. So here there is a this is a very good question to understand. There is this compound given. There are two OH group, two alcohol group are there. Remember, remember this point. When you add acid to alcohol, what happens? Dehydration takes place. Dehydration takes place. Always remember this. Whenever you add HCl, HNO3, HNO, H2SO4, any mineral acid you add, dehydration takes place. Dehydration means what? Loss of water. Okay. So here, first, what is the step? Okay, we'll write the possibility for this step. So this is that reaction. It is reacting with HCl, no? So HCl is what? A good source of what? It is a good source of H plus. H plus means acid, right? So here there is this CH2OH and here it is OH. Now we'll see the attacks. We'll see the attack. Attack means electron rich to electron deficient. So here lone pair of electrons are there. They are more electron rich. They are easily available for the donation compared to the pi bond. If there is no lone pair, you will consider electron rich as a pi bond, like we do in a Markovnikov's rule. There are no lone pair, but we consider the electron rich system to be a pi bonds. Right here, there are pi bond, but this is more free to move lone electron. They are not involved in bonding. If these lone pair were not there, this is the electron rich we'll consider. Right. So here, this is the H plus. This is the H plus which we are adding. So what I'll do is I'll mention the steps over here. First, I'll mention what are the different steps which will take place in a dehydration. First step is actually a protonation. First step is in this reaction. Step one is protonation of alcohol. Protonation means we are adding a H plus. H plus is also called as protonation of the alcohol. Means this is the thing. This is CH2. This is O. H, there is lone pair. This is O and H, this is lone pair. So here, this is your H plus, which is a acid. This is a H plus, which is a acid. Who will attack on this? One possibility is this. I'll mark this process as a A. Any one will happen in any of the reaction. Other possibility is this, A or B. A or B will happen. So to go ahead with this, I will write this process A over here. A possibility is this. So first, let's not consider this. I'll just write this OH because protonation is happening over here. CH2, OH, and the positive charge. This is A. And this is what via B I am writing, means this attack. This is CH2, OH. And this OH and H positive. So in this case, what will happen is that since there is a positive charge on electronegative element, this is a positive charge on electronegative element. Remember, positive charge on electronegative element is positive charge of electronegative elements. Positive charge on electronegative element, sorry, is unstable. That molecule becomes unstable. Remember this. There is a positive charge on electronegative element, positive charge on electronegative element. So bond should be broken, right? So which bond? Let's say if this bond is breaking over here, and obviously this bond will break over here, right? In both the cases, carbocation will be formed. Here, let's assume that, okay, let's understand that this is a carbocation which will be formed over here, CH2 plus and OH. And what carbocation will be formed here? The carbocation which will be formed over here is, it is very difficult to break this bond. I am just showing possibility. If it is breaking by some means, then the positive charge will be formed on pi bond, right? Also, positive charge on pi bond is most unstable. There is nothing as unstable as this. Or impossible, I'll write. Impossible. So this will be in less, this is less stable. So whatever Cl minus is attacking over here will be forming in less amount. This will be a minor product. But major product, what was that? Cl? Yes, Cl. So Cl minus, which is there, it will attack on this. So your main product over here is this CH2Cl, and this is OH, right? This is your major product. But in here, this is major, and your minor product is this. Minor product I'll show here only, or I'll write one more time. Minor product is this. This is very less percentage. This is very less percentage. This is minor product, but this is not asked. Always you should be writing a major product. This is what is asked. The thing about the organic chemistry is, if you are practicing, it requires more and more practice. More you practice, more you will become perfect. Okay. So here, one more question. This is a reaction. It is a HI. This will follow a Markovnikov's rule. Sorry, it is cyclohexene, 1-methyl cyclohexene. If you are adding HI to this, what is the rule? You apply whether it is HI, HCl, or HBr. You're going to apply a Markovnikov's rule for this. So what is the Markovnikov's rule says? The negative part of the adding species will go to the carbon which has a less number of hydrogen. So this is the carbon which has less number of hydrogen. If I write a open chain structure for this, see carefully, open chain structure for this above compound I am writing. This is the open chain structure. This is CH3. Here there is one hydrogen. Here there are two hydrogens on this. So we are putting the hydrogen as per the valency, right? Carbon's valency should be satisfied. Hydrogen, hydrogen. So here there is no hydrogen. So this is the carbon with a less number of hydrogen. So your I should go over here means your final product should be, it is a addition reaction. No, Markovnikov's reaction is a addition reaction. So this is CH3. I will go over here and there will be one more I which will be added over here. We don't show that in a bond line structure. And this double bond will go means in the actual open structure I'll show this way. Here there will be already there was one hydrogen, so one hydrogen will come. This is CH2. You can show it this way. You can write it this way also. I'll write this, right? So this is the product. That's it. Okay. Next question. Question number five over here is this. This question is a halogen exchange reaction. Okay, I'll just say this is halogen exchange reaction here. The product is this CH3, CH2, I. This is a main product, and NABR is a byproduct for this. This is Wilkinson reaction. This is free radical halogenation, but where the things are going to substitute, where Br is going to get substituted in this. Very important. We'll learn this. Understand. See, free radical halogenation proceeds via formation of the free radical, right? So the possibility for this substitution is either this possibility, the Br will get substitute here, or other possibilities that you can think of is this, right? Or other possibility writing a BR, either this or this, and rest is one and same it is. You put BR over here, it is one and same. But it will depend upon where the most stable free radical will be formed. If you go into the mechanism, the free radical formation. Let's see the process of the free radical formation. We are doing question number six. So free radical formation, one possibility is formation of the free radical is here, right? This is Br2. Or other possibility of the free radical is formation over here. Okay, this position is one and same. So which is more stable? This is more stable, and this is less stable. See, stability of free radical is of this order. Tertiary is more stable, then secondary, and then least stable is primary. But over here, both are secondary. This is also connected to 2 carbon, this free radical. Here, this is also connected to 2 carbon. But here, this is more stable because of the conjugation. Here, there is a conjugation. What is that conjugation? Free radical, sigma and pi. Here it is free radical, sigma, sigma and pi. So this is not a conjugation. This is conjugated system. This is conjugated, more stable. So major product will be Br will be getting substituted on this. So your final answer will be over here, this one. Okay. So question, following compounds are given to you. The questions are 2-bromopentane, 2-bromo, 2-methyl butane, and 1-bromopentane. So write the compound which is, so there are three questions which are asked based on this. So you have to identify the compound which is most reactive towards SN2, write the compound which is optically active, write the compound which is most reactive towards beta elimination. So let's do this. So first we'll write a structure of all these things. 2 bromo, first structure is 2 bromopentane. 2 bromopentane is this 1, 2, 3. 4, and 5. And on second position, there is a Br connected. So this is CH3, this is hydrogen. This is what the 2-bromopentane is. Second structure is 1-bromopentane. Let's write over here. 1-bromopentane. I'll write here. 1-bromopentane. 1-bromopentane is this way. 1. This is what the 1-bromopentane. And last is, sorry, second one, 2-bromo, 2-methylpentane. 2-bromo, 2-methylpentane. So here, first is this, second and third I am writing this way. 2-bromo, 3-methylpentane. So 1, 2, 3, 4, 5. So let's consider this is to be second. I am writing Br and 2-methyl. Here it is methyl group CH3. Here one, two hydrogens, and this. So question, write the compound which is most reactive towards SN2. See, SN2 reaction is more favorable for primary, and SN1 is more favorable for tertiary alkyl halide. And this is alkyl halide. I mean this, or a haloalkane. So write the compound which is most reactive towards SN2. So which of this is a primary alkyl halide? So this is the primary alkyl halide, means halide which is connected to a carbon, which is further connected to only one carbon. This is primary, right? If I write this, this is primary alkyl halide. What about this? This is a halide which is connected to a carbon, which is further connected to what? Two other carbons. So this is secondary alkyl halide. What about this? This carbon is connected to this carbon. Sorry, this halide is connected to this carbon. This further connected to three carbon. So this is tertiary alkyl halide. So answer is primary alkyl halide. So answer over here is primary alkyl halide. Means which compound? Green color I am using. No, it is 1-bromopentane. Means this is the answer for the first one. Okay, this is the answer for the first one. Write the compound which is optically active. Optically active means the compound there should be at least one chiral carbon that is optically active. So in which case there is a chiral carbon, it is the this structure. This is that structure in which there is a one carbon which is chiral. What is the meaning of chiral or optically active carbon? Chiral or optically active carbon, there should be all four groups attached to it should be different. This is that carbon in which all four groups are different. One is methyl, other is Br, other is hydrogen, and this is propyl group. All four groups, this is one group I'll consider, this is another, this is second, third, and this is fourth group. All four groups are different. That's why this is a chiral carbon in this molecule, and this whole molecule is optically active. This is not a chiral because here two hydrogens are similar, that's why it is not a chiral. This is also not a chiral, this is also not a chiral. Then all four groups attached should be different. Here if you see, none of the carbon is chiral because here Br is there, this is butyl is there, and there are two hydrogens which are similar. This is also not a chiral. This compound there are two methyl group which are connected, which are similar. So chiral is what, or optically active compound which have all four groups attached to it are different. So the answer for the second one is 2-bromopentane. This is the answer. 2-bromopentane. 2-bromopentane. bromo, pentane. This is the answer. Then last is write the compound which is most reactive towards a beta elimination. Now, what we'll do is we'll write the eliminated product, dehydrohalogenation. We'll write the most stable product of the dehydrohalogenation. Okay, so here we'll do this. You have to write the alkene which is most stable alkene. If you do the dehydrogenation or if you do the beta elimination, if you do beta elimination, right? Means what will happen over here is that you will get a most stable alkene. Means this is the hydrogen. You are going to remove this HBr. You can remove this also, but that is not going to give you a most stable alkene. So what is the alkene you are going to have? CH3, CH2, C. There is hydrogen here. One hydrogen. CH double bond CH CH3. Two alkyl. Okay, we'll discuss this later. Here, one hydrogen and one Br we are removing. So which hydrogen and which Br we are removing? We are removing this. This structure is written this way. This is H and this is Br. So we are going to remove this in a beta elimination. We are going to do this for a beta elimination. Beta elimination. The compound what you are going to have is this CH3. And what is the answer for this? Uh, it will remove this hydrogen. For a beta elimination, I will write this hydrogen. So there is a removal of HBr over here. After beta elimination, the product what you will be getting is this CH3, CH2, CH double bond, CH3 and CH3. Here in the last compound, if you see, there are three alkyl group across a double bond. One, two, and three. Here across a double bond, there is just one alkyl group. And here there are two alkyl group. So which alkene is most stable? This is most stable alkene, most stable alkene. So one which will give you most stable alkene, that will be most reactive towards a beta elimination. So the answer for this is this. Identify the chiral molecule in the following. What is the meaning of chiral? I have discussed briefly in the previous question. Chiral, chiral molecule means optically. Chiral molecule means optically active. Optically active means which can molecule can rotate. Molecule can rotate. Molecule can rotate plane polarized light. Okay. So optically active molecule or molecule which can rotate a plane polarized light, that is what a chiral. How, what is the condition? There should be presence, there should be presence of at least one asymmetric carbon. Asymmetric carbon means what? What is the definition of asymmetric carbon? Asymmetric carbon. All go all four groups attached to it should be different. Okay, all four groups attached to it should be different. So this molecule which is given, I'm going to write a open chain structure for your understanding. Then we'll identify which carbon is a chiral and which is not. So just make a note of this. I'm going to delete this. Yeah. So we'll write this first structure. Okay, this A structure. I'll call this to be A and I'll call this to be B. So A structure I am writing. So this is that carbon. This is a first carbon. Then next, this is the next carbon. This is a another carbon. So terminals. This is also carbon. This is carbon. This is carbon. This is carbon and carbon. So next, this is the carbon, and here this is the carbon. Understand? Huh? So here, what is there on this carbon? There is OH. This is given. So what they have not shown, what we don't show in a bond line structure is the hydrogen. So here, this is hydrogen. So we are going to put this required number of the hydrogen. Here, this is hydrogen. So here, there are three hydrogens. Hydrogen. Here, there are three hydrogens. Hydrogens. On this, there is this hydrogen. So among this, which molecule is there a chiral center? If you see over here, if you see over here, this carbon is not a chiral because three similar groups. This carbon is also not a chiral because three similar groups connected to it. Let's talk about this later. This molecule, this carbon is not a chiral because three similar hydrogens. Now coming to this, yeah, we'll do this. So this is also not a chiral because this group is a methyl and this group is also methyl. Two similar groups are connected. There shouldn't be all four groups attached should be different. This is also not a chiral. If you think of this, this is hydrogen, this is OH, this is methyl group connected, and this is some other bigger group connected. So all four groups are different. So this carbon is chiral. I will mark that this carbon is a chiral over here. This is about the structure A. What about structure B? Structure B is this. This is that carbon. This is next carbon, 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 and this is carbon. And here this is the carbon. This is OH. So what is this? As I have explained, this is H3. It is not a chiral. These are not chirals. These are not chiral. This is also not chiral. Here there is a hydrogen, one hydrogen. How I decide that? So that all the carbons should have four bonds. This is also not chiral because these two groups are similar. This carbon is also not chiral because these two groups are similar. But what about the center one? Is it a chiral? No, this is also not a chiral. There is one hydrogen. This hydrogen and OH are different. But if you see this group and this group, they are same. So in this case, in compound B, there is no any asymmetric carbon. So question asked was identify the chiral molecule in the following. So this is the molecule which is chiral, means this is optically active compound. Optically active compound. Next question is complete the following chemical equations. So here this is C6H5Cl, means I'll write in a proper molecular formula, structural formula. C6 C6H5Cl. So this is C6H5Cl, means we are talking of chlorobenzene. Okay, and this is CH3COCl. CH3 C double bond OCl. In the presence of anhydrous AlCl3. The product form, I will write the product. The product, you can guess the reaction. What is the name of this reaction? The major product I am writing. This is Cl. C double bond O CH3. This is major product. And the minor product is this. This is major and this is minor. Now let's go into the mechanism. The name of this reaction is Friedel and the Kraft acylation reaction. Acylation reaction. So mechanism for this mechanism is not will be not asked for exam, but you should know the mechanism how what happens. Mechanism. Step one is formation of electrophile. Formation of electrophile. This is the first step. So it is this. It is CH3, C double bond O, Cl, and it is AlCl3, right? AlCl3. This is a Lewis acid, which is in always need of electron. So this is electron rich and this is electron deficient. So what is formed is this CH3, C double bond O plus and AlCl4 minus. So this is the electrophile which is formed, right? Step 2 is substitution by electrophile. Electrophile will get substitute on a benzene ring or a chlorobenzene. We start with this. This is chlorobenzene. Okay, and this group is again what? This chlorine is orthopara directing. I'll write here. This is orthopara directing to electrophile. So incoming electrophile will get substituted here, here, or here. It is one, these two positions are equivalent, right? So in the presence of the electrophile, CH3 C double bond O plus. Actually, here, what is the meaning of benzene? Everywhere there is a hydrogen, no? Everywhere there is a hydrogen, which we don't show. Understand this? Okay, everywhere there is a hydrogen, which we don't show. So electron rich, I'll show this attack. It will attack on this carbon, electron deficient, right? And the product, the intermediate which will be formed is this double bond here. Here it is Cl. These hydrogens are there which we don't show. Okay, I'm just showing for your understanding over here. So this is a hydrogen and this is going to form a new bond, this carbon. That new bond is this. It is connected to this, no, COCH3. But this carbon is going to lose its one electron in that formation, positive. So to gain the like stability, aromaticity of the benzene is lost. No, over here to gain that aromaticity back, this hydrogen will be lost further. And the final product for you, major one only I am showing. Same thing you can do for the minor one. So this is Cl, this is C, double bond O, CH3. That's it. So this is the major product.